Hi, everyone, and welcome. My name is Rebecca Patterson, and I'm the Program Coordinator for AIA California. Thank you for joining us for today's webinar on ADUs. As you get settled, I will go through a few reminders. Please use the Q&A to ask any questions for today's panelists. And with the Q&A feature, attendees can like a question to move it to the top of the list. And as always, the webinar content and additional resources will be available on the AIA California website shortly after the session. Today's session is focused on how to integrate climate responsive design solutions and technologies into ADU designs. The session qualifies for 1.5 AIA HSW learning units for those watching live. AIA California staff will report those units for you once you have finished the session. This webinar also meets the ZNCD MCE requirements. Links to downloadable certificates will be provided within a follow-up email after the session. Our moderator for today's session is Jennifer Kretschmer. Jennifer has a Bachelor of Architecture from Cal State University, San Luis Obispo. She is the owner and principal architect of J. Kretschmer Architect, where she focused the last 3 years on the zero net carbon design of small projects. She is also an AIA 2030 commitment signatory. Jennifer, thank you for being here today. I will hand it over to you.
Thank you, Rebecca. I'm excited to share this information on our climate action initiatives. As Rebecca mentioned, I am a signatory of the AIA 2030 commitment. The latest climate data tells us that reducing carbon emissions is not enough. To make the biggest impact, we must all commit to net zero emissions by 2030, a path that requires strong, immediate action. Since the built environment creates a staggering 40% of the world's emissions, architects, engineers, and owners play a very key role. The AIA 2030 commitment is an actionable climate strategy that gives us a set of standards and goals for reaching net zero emissions in the built environment. If you are interested in learning more, Rebecca will be adding a link in the chat box. Now, I would like to briefly introduce our presenters for today. You will hear from Kanika Sharma, who is the Associate Principal and USW Sustainability Lead at Integral Group, as well as Chair of the USGBC LA Building Decarbonization Committee. We'll also hear from Charles Ely, an architect, mechanical engineer, and author with 40 years experience in energy efficient and sustainable design. Brian Selby, the principal of Selby Energy Inc. and part of Energy ACE Resources, will speak today on more Title 24 energy compliance. Richard Young, who is the director at Frontiers Energy's Food Service Technology, will be our last speaker. After hearing from each of the presenters, we will answer as many questions as time will allow. On today's presentation, we're going to get started with our first presenter. So Kanika, welcome, and please take it away.
Thanks so much, Jennifer. Hi, everyone. Nice to be here, and thank you all for joining. I'm going to share my screen. See if that works. Okay. So like Jennifer mentioned, my name is Kanika Sharma. I am an associate principal and the US West lead for sustainability lead for Integral Group. We are a deep green engineering firm with over 100 net zero energy, net zero carbon projects under our belt, as well as many of the LEED Platinum, Bell Platinum certifications, and have a deep focus on decarbonizing our buildings. And almost every project that we take on, we aspire for it to be all electric and not engineer gas into our buildings. So we are a group of highly passionate people, as so are all of you. And so today I'm going to be talking about why we need to move towards decarbonization, and Jennifer sort of hinted towards it, and that's one of the big reasons why you all are here. But just, you know, starting the discussion from a high level and then moving on to the operational carbon and the metrics that help us and the pathway that helps us to get to that net zero carbon emissions. for operational carbon, and then also touching briefly on embodied carbon, which is another key piece that will become super critical as we start to decarbonize more and more of our buildings and make them all electric. So moving on, via decarbonization, I guess, like, as we are all well aware of the latest IPCC reports that came out this week, also, there is a significant need for us to reduce our carbon emissions. And this color scale that you see up on your screen shows the annual global temperatures from back in 1850s to 2017. And it's pretty clear from here that, we know that the climate is warming and the temperatures are rising, as indicated by the deep red shades on this slide. And in order for us to meet our 2-degree target as established by IPCC, we need to be reducing at least 80% of our carbon emissions by 2030 and getting to net zero pretty soon after that. And we hold that responsibility majorly because, again, like Jennifer mentioned, the building industry, or our global built environment, contributes to up to 40% of these carbon emissions. So by 2050, it is mandated, or that's the goal that we aspire towards, set by the UN. All new and existing building assets must be net zero across all of their whole life carbon emission stages. So that includes not just the operational carbon emissions, but also the embodied carbon emissions. And here you can see on this pie chart, 28% of the carbon emissions are associated with the building operations, which is what we call the operational. And then there is another huge chunk, almost 11%, that constitutes the embodied carbon emissions from the building materials and constructions. And I'll go into a little more detail on the subsequent slides here. But just high level, so when we talk about carbon emissions, what does that really mean, and what are we talking about? So carbon emissions are all of these greenhouse gas emissions which are responsible for global warming, and we typically see it being represented as kilograms carbon dioxide equivalent. And what that equivalent means is that it also locks in or captures all of the emissions from some of these ancillary gases like methane and nitrous oxide and HFCs, which are some of those refrigerants and some of the other gases. And all of that is being back calculated to say how much of that impact equates to a typical impact from carbon dioxide. And so whenever you see that kilogram carbon dioxide equivalent metric, that actually captures all of the carbon emissions from these other gases beyond just carbon dioxide. And that's the metric that we use when we talk about carbon emissions globally as well. And over the life cycle of a built asset, there are different parts and stages that are involved. So when we talk about whole life carbon emissions, or when you hear that term, that essentially means that we want to be accounting for the carbon emissions associated with the overall whole life cycle of a building. So that's the operational carbon piece and also the embodied carbon piece. For operational carbon emissions specifically, as shown here in orange, those are the carbon emissions associated with the energy and water use during the building's lifetime. So the in-use phase of a building, whatever emissions are emitted by the space heating or water heating and the equipment that uses electricity, those are the carbon emissions that get accounted for in the operational carbon piece. Whereas the embodied carbon piece is all of the other things. So there are significant carbon emissions that get locked into a building when the materials are being installed, when there are repairs happening, when there is some kind of maintenance that needs to happen, a retrofit. So all of the other carbon emissions that are associated with the production, construction, use, and the end of life stage of a built asset is categorized as embodied carbon. And these materials, the impact that they have can be quite significant. And the studies that we've done internally actually shows that it could be well beyond the operational carbon. And Architecture 2030 also has a really great graphic on their website where they show the cumulative impact of these emissions over the life of a building could actually be almost split 50-50. So that's something that we need to be extremely cognizant on moving forward. And these material impacts, so they have these environmental impacts associated with the mining of the the raw material, the extraction of all of it, the transportation of that to the site, and then manufacturing in the factory, then transporting that to the building site, installation at the building site, and then its end of life, dismantling, demolishing, disassembly of that material. And embodied carbon is becoming more and more relevant, especially because we are doing a better job at reducing our operational carbon emissions. And so as the grids start to get decarbonized, and California has a goal of decarbonizing its grid by 2045, and when projects are designed to be net zero energy, the operational carbon piece sort of starts to shrink, and the embodied carbon piece, like you can see up here, like that starts to become really significant. And over the life of a period of a new building, it could be as high as 70% also in some cases when it's a net zero energy building. And most of this embodied carbon gets locked in upfront. So this big red bar that you see up here, that's the upfront embodied carbon emissions that get locked in at the time of construction of the built asset. And so when we think about the time value of carbon, sure, we can, through the decarbonization strategies of operational carbon, start to reduce those emissions over time. But if we don't address this key piece of the carbon emissions that we are locking in when we are constructing our new buildings right at this moment, then that just remains there. So we need to be cognizant of that and selecting consciously materials that don't have a high embodied carbon associated with it. And then over the life of the period, like I mentioned, there are different spurts of these embodied carbon emissions that happen as there are repairs happening or refurbishment or retrofit that happens in the built asset. And when you hear this term zero carbon in our profession, most of the time what people are really talking about is zero operational carbon. So that distinction needs to be very clear. There are claims of some buildings being called net zero carbon, but what they're essentially talking about are net zero operational carbon, unless they are purchasing offsets to offset the embodied carbon emissions from their buildings. But there are a lot of efforts that are being made to get to that zero operational carbon. So that's the great news here. So we can already see in California, there are over 54 cities that have already committed to either implementing the REACH codes or having some kind of an enforcement mechanism and regulation in place that will enable new construction and in some cases existing built assets to not have gas in their buildings and move towards electrification. And what all electric designs allude to, and Brian and Charles are going to cover this in much more detail, are looking at our equipment for space heating and hot water, moving to a heat pump equipment design, getting rid of the gas stove tops, and Richard's going to talk about that one, and moving to induction cooktops in the buildings. And then all of this backup power or ancillary uses like clothes drying or even charging your vehicles, getting to EV vehicles, these all fold in when you talk about a comprehensive all-electric design for the building. And the metrics that we use to enable us to make comparisons between our proposed design and the baseline EUI, baseline design is called EUI. So EUI is the energy intensity, and some of you may be familiar with that, but this graphic just gives you a quick snapshot of how that is being calculated. So you lump together all of the different energy end users for your building and what the overall loads are for that. You divide it by your gross building area, and that spits out this absolute number, which is called an EUI for your site. And if there are renewables installed on the project, that enables buildings to actually zero out that overall EUI and get to that net zero, again, operational carbon, not overall carbon. And a quick pathway to performance that some of you may be familiar with, especially when we talk about net zero energy or net zero operational carbon buildings, is you set that benchmark, which is your baseline EUI, here shown in red, and then you start to adopt these strategies at various stages of design, starting with optimizing massing and design with passive design strategies, incorporating daylight and natural ventilation and optimizing your envelope. So figuring out how we are implementing or adding all of the passive design strategies, incorporating all of the passive design strategies first, reducing your EUI, then moving to the active design strategies of looking at high performance HVAC systems, high performance induction cooktop systems, and then reducing the other plug loads such as lighting or receptacle loads through various devices that help you optimize and monitor the load distribution. So you get to that final EUI, which is already like hopefully significantly lower than your baseline EUI. And then you offset that completely with the help of PV. So if the building is generating excess PV as compared to the building's consumption needs, that's when you get to that net zero number. And there are various tools available out there in the market to help you model that more accurately. But if you want to do a quick and dirty calculation for what that EUI looks like for your region and how you can establish the baseline and the proposed EUI for your building, Zero Tool by Architecture 2030 is a great tool to just start with. So you have all of so there's a link out here, and I can also post that link in chat after my presentation. But anything that's represented by a red asterisk here are the inputs that you need to add into this calculator. And then you set your goal for how much percentage you want to reduce from the baseline. And then it gives you this kind of like gradient chart to show you how that reduction can be made possible and what is needed. And then you can go back to that pathway to performance slide and start to implement some of these measures for you to achieve that lower end of the EUI for your project. But so that's operational carbon. But what about embodied carbon? So the logic behind calculating embodied carbon is pretty simple. It's not hard science. It's essentially looking at your material quantity estimate, looking at the embodied carbon of those material units, multiplying that, and that spits out what your total building embodied carbon is. And just as EUI is a metric to calculate the operational carbon intensity in your building, kg CO2e, or global warming potential in this case, is the way of representing what the overall embodied carbon of your built asset is throughout its life cycle. So just as an example, if you have about 100 kgs of steel in your building, and we know the embodied carbon of steel is 2.97 kg CO2e per kilogram, that gives you that 297 kg CO2e as the embodied carbon number for that overall steel that's used in your building. So if you add all of those materials up, you should be able to have a pretty good estimate of that overall embodied carbon in your building. And again, there are various comprehensive sources that are available or sophisticated modeling tools that are available for calculating LCA as well. But for your purposes, for when you are designing an ADU, if you just focus on these three databases that are free and available for you to use, that should set you up for success. So EC3 is a tool where you can go in and filter out products by the lowest to the highest embodied carbon, and you can do product comparisons between two similar products. So for example, if you're looking to see whether Owens Corning or Johns Manville has a lower insulation product, you can input your product information in the tool and it will show you exactly what the differential is between those two products. Carbon Leadership Forum is your go-to source for anything related to embodied carbon 101, any tools that are available, educational resources that go far beyond what I will be covering in this presentation today, and also for you to figure out what that good, better, best baselines are for many of your products like insulation, or if you're using any kind of flooring product. And then similarly, Carbon Smart Material Palette is a ready resource that enables that comparison at a much higher basis. So for example, if you are looking to choose between mineral wool insulation or fiberglass insulation, which product has generally a higher embodied carbon in it. And an example of this is something like this. So you have this graphing on for other similar product categories where they would show you through this gradient, like if you were to select a high density spray foam, that automatically means that that product has a much higher embodied carbon than if you were to select a natural insulation product such as hemp or cork in the building. And a lot depends on how the building is actually designed as well. So a lean architectural design would automatically mean that you have lower embodied carbon, because the less materials, the less embodied carbon you are locking into the building up in, in the initial stages. But key things that you need to be focusing on when considering the construction aspect of, or the constructability of the product of the building, is focusing on low carbon concrete design mixes. So this is critical, especially like this will give you an automatic reduction of up to 10% if you only select concrete design mixes that have lower embodied carbon. And there are many concrete suppliers that will actually produce a verified environmental product declaration or a certificate that actually shows what the calculated embodied carbon of their concrete design mix is. And rule of thumb is like the less the cement in the mix, the lower the embodied carbon. So cement is the ingredient in that overall concrete that has the highest amount, that contributes the maximum embodied carbon of the concrete design mix. So the lower the cement in the mix, the lower the embodied carbon in that mix. Then also finding steel that has high recycled content. So if there are any rebar or any other steel that goes in the facade, finding sources where they already have certificates showing that it has a high recycled content would mean that the steel is lower in its embodied carbon. And then using some of those sources that I mentioned on the slide previously to find low carbon product alternatives for insulation, flooring, drywall, and doing those quick product comparisons will give you a good gauge of which products that are available in the market currently that you can install with similar technical performance as what is needed by your specifications and still have like lower embodied carbon. And then just my last slide, a quick sheet on overall. So what can be done to reduce embodied carbon? One of the critical things is, like I mentioned, optimizing for material and structural efficiency. So less materials equals less embodied carbon in most cases, unless you select more materials with natural elements to it. Then focusing on a carbon smart palette and making sure to select products like wood, which are carbon positive or sequestering materials, and FSC certified wood in lieu of like a steel and concrete structure would actually help reduce your overall embodied carbon significantly. And you will also be sequestering all of those carbon emissions when you create a mass timber structure. And then also focusing on reuse or repurposing existing building components wherever you can would mean that you are using building components that already have that embodied carbon locked in. So you are not creating new demand for newer materials and adding more embodied carbon to that. Then using salvaged or recycled materials, like I mentioned, especially in the case of steel or aluminum, if you can find products with high recycled content in it that would have low embodied carbon. And then this is one critical aspect which sometimes gets missed when we talk about embodied carbon, but designing for durability and maintenance. So making sure that the finishes and the materials that are being selected are being treated well for durability and maintenance and longevity, because that would really that would prevent people from replacing it more often, and that equates to less embodied carbon over the life of the building. And then if you could find materials that are locally sourced or produced regionally, that means that they reduce transportation emissions and can actually help reduce the overall embodied carbon in your project. And last but not least, designing for standard sizes to reduce wastage of materials. So if we are doing a modular design, replicating that modular design to mimic the actual module of the product that is being installed will result in less wastage and then also cost savings significantly for the project. So with that, I'm gonna close, and I think we're gonna do Q&As later, but I'll pass it back to you, Jennifer.
Thank you, Kanika. We're going to move on to our next speaker, but I would like to say that please use the Q&A to chat in whatever you would like as a question. We'll get to questions at the end. Let's see. And take it away.
All right, thank you. Can you see my screen okay? Yeah, this is a small project. I want to talk about some of the problems we had with this ADU. It's only about 500 square feet. It's separate from the main house, and it's all electric. The fact that it's separate from the main house means that as far as the energy standards are concerned, it's treated like it's as its own little separate single family home, which presented a few problems that Brian can talk about. One of the issues we had was the requirement for solar. The width of this ADU is only 18 feet, and to meet the homeowner association requirements, it needed to be a hip roof. So the south roof area is really quite limited. But what we were able to do is to install an 8 kW solar system on the main house, along with battery storage. And we worked with the building department, and they agreed to basically combine these two building permits for the purposes of complying with the solar requirement. Another issue that we had was water heating. So this is all electric, and we wanted to use a heat pump water heater. And there are too many water heating loads in this little ADU. There's a shower and a lavatory, and a bar sink. That's basically it. There's no dishwasher. There's no clothes washer. Anyway, the smallest unit we could find was about 40 gallons. And one of the issues is that it's these have to be located, if they're indoors, they have to be located behind louvered doors so that they can communicate air with the space. And they're kind of noisy. So I think in hindsight, I would have probably located that water heater in the refuge area outdoors, and either that or ducted it to the outdoors and used a solid door. Anyway, that's something you need to pay attention to with ADUs if you're using heat pump water heaters. They are a bit noisy. Richard can talk more about this, but there's a tiny little kitchen. It's not, this is the whole thing right here. And there's not a lot of choices for small appliances. There's an under-counter refrigerator, a microwave that also has a fan, and an induction cooktop. And that's basically it. The fan is actually required by code in California, so that had to be vented to the out of doors. Another issue was HVAC. This ADU has a split system air conditioner. There's a unit that sits outside, and when I designed it, I designed the interior unit of the indoor unit so that it was entirely within conditioned space. It was below the insulated ceiling, and that solved a lot of problems in terms of insulation. But the HVAC contractor changed this, and he put ducts in the attic. And anyway, this created some compliance issues, which Brian can talk about a little bit more. But basically, once you have ducts in the attic, you have to have insulation both at the roof of the attic and also at the floor of the attic. And since this ADU is only 18 feet wide, the ventilation area up there is pretty small. Combine this with hip roofs on 4 sides, and anyway, we were able to kind of work it out with some special products and a dormer, but this did kind of create that issue. This unit was the ADU was completed in late 2020, and I collected electricity consumption at the meter over the last 3 years, and you can see here that until the solar system was commissioned about a month or so before the ADU was completed, and once that was commissioned, the electricity use went negative. That's the green at the bottom. The ADU was completed a month or so later, and since that time, it's been we've exported more electricity to the grid than we've drawn from the grid, as witnessed by the area of the green bars versus the area of the red bars. So this is actual consumption at the meter. It's not modeled data. Brian can talk a little bit more about the modeled data. So that's it. It's a simple little project. We did have some issues with the homeowners association when it was first presented to them. They said no, you can't do that, and but we cited the legislation in California that enables ADUs, and they of course had to back off a little bit. There were some other funny things that went on with the homeowners association. The exterior walls have there's waterproofing, and then there's exterior insulation, and then a thin set stucco over that. And the waterproofing was a liquid applied membrane, which was bright pink. And so when that went up, we got a bunch of phone calls from the homeowners association saying, "That's not the color of the unit, is it?" And no, don't worry. This is just a temporary color. It'll be covered up. Anyway, that's it. I'll stop there and pass it on back to Rebecca and to Brian. Stop my screen here. Okay.
Thank you, Charles.
Sure.
Yes, Brian, we'll talk about energy modeling.
That's great. Thank you, Jennifer. And thank you, Charles. For those of you who don't know me, I'm one of the Energy Code ACE instructors. Energy Code ACE is a brand and website sponsored by the investor-owned utilities, PG&E, SoCal Edison, SDG&E. So all of our training for free, resources for free, tools for free, really focus in on reducing compliance issues with our energy code. So Today, this is a perfect segue into some of the topics I wanted to cover. I did have the pleasure to work with Charles on developing the compliance for his ADU, and it was very challenging. And I have to say, Charles, you're not alone in that department. There are many folks struggling to get ADUs, especially our smaller dwelling units, in compliance with our energy code for many different reasons. And I want to come into this conversation and share some of the challenges that you might be facing out with doing these types of dwellings. Now, before I get started, I want to just kind of level set here. I know Charles talked about ADUs and how they're classified within our energy code. They're treated as either new construction or an addition based on not only the proximity to the existing structure, but whether or not it's being converted from an existing space like a garage or an unconditioned space to a newly conditioned space. So I wanted to cover that real quick. Just keep in mind that all newly constructed dwellings, whether they're classified as an addition or new construction, must meet all those indoor air quality requirements for ventilation, like Charles was talking about, the local exhaust for the kitchen hood, having filtered recirculation air, supplying fresh air from the outside. So that said, as far as what constitutes a classification of either new construction or addition simply boils down to these questions. Is it a conversion from an existing space? In any situation, whether that dwelling new ADU is attached to the existing structure or detached to the existing structure, a conversion from an existing unconditioned to newly conditioned is always considered an addition. Same goes for converting an existing conditioned space, like an existing bedroom in a house, to an ADU. That would also, well, that would actually be considered an alteration, and only the altered components would apply. But when the project is determined to be classified as new construction, again, depends on whether it's attached to the building or not. So if it's detached, built new, no building has ever existed in this location before, then it's classified as new construction. If it's attached to the dwelling, you're adding on to an existing house, or even if you're adding on to an existing garage, it's still considered an addition. And the significance about this is the energy code treats new construction and additions separately. They're separate portions of the code. So just want to level set that from the beginning so everybody has that understanding. Couple of things I wanted to cover. Some of the design challenges that you folks are going to face designing ADUs for compliance with our energy code. Oftentimes, you're not going to have a choice on the building orientation or the location of that new ADU on the lot, pretty much dictated by the site. There might be existing structures that you have to work around, property line setbacks, utility setbacks. Charles brought up homeowners association requirements may dictate the design, having to put a hip roof on a house that you didn't necessarily account for in your design. Those are all impacts overall on the energy performance and how certain strategies for either insulating or mechanical or water heating strategies are going to dictate your design and whether it's going to comply or not. Also, available utilities. Now we're talking about all electric dwellings, but in some cases there may be some gas appliances there. So those are all constraints on designing ADUs for compliance with our energy codes. Now, all of these slides, I've added some design considerations that you might want to think about. So in these types of situations, if you have an ADU that you can't design the best possible strategy for taking advantage of placement, orientation, so forth, that you may not be able to take full advantage of those features, and it may impact your overall compliance. And the types of features I'm talking about are built-in overhangs, shading that might reduce the amount of solar heat gain that particular building might have, taking advantage of passive solar design and so forth. So those are some design considerations based on the site. Now, moving through the building here, the minimum PV system sizing requirements are set by our prescriptive code, meaning that based on the size of the dwelling, how many dwelling units there are, and the climate zone that it's in, it establishes the minimum sizing requirement. Those are all laid out in our energy code, table 150.1a, and specifically section 150.1c14 addresses the solar PV requirements. Oftentimes, these buildings are so small that the minimum size requirement are often too small to be cost effective. So what happens? We have to get a little bit more creative. In Charles's situation, where they were able to utilize some of the proposed PV system on the existing house to provide the adequate sizing or capacity of that PV system to meet the requirements for the ADU. So keep in mind that PV system sizing requirements in our energy code are based on a mixed fuel building, meaning that it has gas, space heat, water heat, everything else would be electric. And that's just so we can level set. So if you're having an all electric home or a mixed fuel home, the PV system size is going to be exactly the same. No difference in those. So now that's not being slated to change for 2022. We still have the same requirements. So we need to take that into consideration when we design our buildings. So you can add PV to an existing building. You just cannot use existing already installed PV system on an existing building to satisfy the new construction requirement for PV. So the Energy Commission is pretty clear about that. We've had a lot of discussions with them. So keep that in mind. Make sure that there's adequate space either on the roof of the dwelling that you're building. It could be on any other structure or located anywhere else on that property to satisfy that requirement. So it could also be part of a community shared solar program. And currently there's only one of those in existence. That's in the SMUD territory, Sacramento territory. So I'm going to keep moving through these. If you have questions, you can ask those in the question and answer column, and we'll get back to those in a little bit. Another one of the design challenges for ADUs is the one that Charles pointed out. ADUs typically have smaller footprints with attic areas having less vertical clearance than a typical single family home. Even if the roof pitch is fairly steep, you're still dealing with clearance issues. You can see by the detail over here that our prescriptive requirement for attics in the hotter climate zones, talking climate zones 4 and 8 through 16, there is a prescriptive requirement for a minimum of R38 ceiling insulation with an added R19 insulation below the roof deck. Our energy code calls this a high performance attic. And the idea behind this is to reduce the amount of heat in the attics, therefore reducing the amount of heat transfer into our conditioned spaces. This strategy works great, although when you have limited clearance, it gets very, very complicated. There are an alternative choice to place the ducts and the air handler inside of the conditioned space, and then you're not going to be compared to that below roof deck insulation. But that's not always a choice. Some of the design considerations that you want to take in account for is that if you're not going to install that below roof deck insulation, just understand that the performance approach, when we model that building and analyze it, that it's going to be a penalty for not doing that. And in many cases, in those hotter climate zones 4 and 8 through 16, that penalty is pretty severe as far as what your proposed design energy budget is. So it's always good to keep that in mind. There are ways to design around that and different material choices. Also, there's a penalty for rafter roof design. There are no prescriptive requirements for rafter roofs. Therefore, it falls back to being compared to a building in your standard design with an attic roof. And by the way, if I'm covering any topics, energy code topics that you're unfamiliar with, I'm happy to answer questions. I'll put my email address up at the end, and you're welcome to ask questions or check out Energy Code ACE. So you can come to one of our classes and we can go a lot deeper into some of these requirements. Next was fenestration. So ADUs typically have higher glazing percentages. You don't necessarily want to or cannot reduce window area less than what the egress requirements are, or providing natural light. So these this is a pretty difficult design challenge to overcome. If you look at the standard design or the prescriptive requirements from our energy code, the glazing percentage is limited to 20% of the floor area. So the glazing area divided by the conditioned floor area will determine what the total glazing percentage of that residential building is. Likewise, if you're in one of the hotter climate zones, you see that down at the bottom, everything except climate zone 1, 3, 5, and 16, then you also have a limited amount of west-facing glass. Now, it doesn't mean that you can't build a structure that has more glazing than that, but just understand that anytime you cross that 20% threshold or 5% threshold, if you're in some of those hotter climate zones, then you're going to get an energy penalty for that. A good design consideration is to make sure that you factor in shading. South-facing windows, obviously. East-facing windows have some benefit. West-facing windows have also some benefit of the shading, but as you know, once that sun angle gets really low in the west, it's really hard to control the amount of heat-causing light that's going to enter that building. So moving to a spectrally selective fenestration product, low emissive coatings, the lower the solar heat gain coefficient, the better properties that window has to filter out that heat-causing light. So mechanical system challenges. I know Charles and I faced some changes midstream on his ADU project. We had originally designed in a ductless mini split. And under our current code, there is what's called the VCHP credit, which is called a variable capacity heat pump. All of our mini splits, multi-splits, even the variable refrigerant flow systems fall into that variable capacity heat pump. Extremely efficient, right? And in the past, our energy code penalized that type of technology because it didn't act and look and function like a conventional central system. So it was penalized. Recently, we had a compliance option to provide a credit as long as you fit the prescribed method and qualification for these various units. They give you a really nice credit. And you maybe have designed some buildings and taken this VCHP credit. And for an energy consultant, this is a magic button. We can click the VCHP credit and magically everything complies. But there's some specifics about those systems that need to be met in order to qualify for this. And if you don't, then there's going to be a lot of issues come time to provide the documentation to prove that it still complies. So a couple of things. The VCHP credit requires location of indoor units. That's the fan coils that are located inside. To be entirely within the conditioned space. So if you have a cassette style that's stuffed up into the ceiling, you don't want the wall mounted ones like I'm showing here. There has to be some special consideration to make sure that they're within the air thermal boundary of that envelope, the interior conditioned space. So some special considerations there. Additionally, you have to have airflow to all habitable spaces. So living spaces, bedrooms, dining rooms, kitchens, bathrooms, hallways, closets, those are all exempt from meeting that requirement. So in addition to that, there has to be a wall-mounted thermostat for heating cooling zones that are greater than 150 square feet. So not just the remote control that sits in a cradle stuck to the wall, it has to be a hardwired fixed thermostat to the house. So now some of the design considerations I like to recommend, if you're planning to use a ductless unit, no ducts on your mini split, then that's a slam dunk for meeting the VCHP credit. As long as you have the 150 square foot inhabitable spaces and the wall mounted thermostats, it's an easy compliance credit to take. Not so easy with ducted systems. They have to meet a low static pressure requirement, and fewer of the manufacturers are choosing to certify their products for a low static pressure. Therefore, very limited in the market what could actually qualify for this. So keep in mind too that in order to take this credit, the variable capacity heat pump credit, that it also requires third-party HERS verification. So HERS rater would need to go out and verify that these measures or qualification measures have been met. One thing that a lot of folks don't really think about much is ventilation cooling. Our energy code has a prescriptive requirement for it. Climate zones 8 through 14 require ventilation cooling. And if you're not familiar with it, I don't want to spend a lot of time on it, but essentially you're exhausting the indoor air to the attic space. And the makeup air is going to be coming through a window or a door. When the outdoor ambient temperature is cooler than the indoor temperature, which occurs quite often in some of these climate zones, then not necessarily free cooling, but less expensive cooling can be obtained through this type of unit. Now, it does require a minimum attic space, minimum airflow of the whole house fan unit, 1.5 CFM per square foot of floor area, and minimum sizing for the attic ventilation to accommodate that exhaust air being exhausted in the attic. So there are also options for directly venting the whole house fan to the outside. That is another design consideration. But keep in mind, if you choose not to do this and you're in climate zones 8 through 14, then you're going to get penalized for that, meaning that the more penalties we have on our proposed design make our buildings no longer meet our energy budget. So we've got to keep that in mind. It doesn't mean you have to install one, but there are some penalties that you're going to incur for doing that. Lastly, some of the design challenges, and I know we talked about this with Charles's case study here, the ADU. Heat pump water heaters are difficult to locate inside. There's a lot of issues around heat pump water heaters. Space is one of them. They do take up a considerable amount of space once you factor in the clearances. They produce cold, dry air, and that's not necessarily desirable condition inside our homes. So it's important to take those types of considerations into account, either ducting that incoming air and outgoing air to the outside, or in some cases, you could use a remote compressor. The Sandin units, if you're not familiar with those, really popular. They've got an indoor tank and an outdoor compressor. They're disconnected, but work as one system. So likewise, heat pump water heaters can be noisy. I know I saw some of the chat discussions here about, no kidding, they can be noisy. So keeping them away from bedrooms, living spaces, likewise, keeping heat pump water heaters that aren't ducted to the outside away from thermostats. You can impact your energy usage if that heat pump water heater is outputting cold, dry air in a heating season and it's located next to your thermostat. It might confuse your system into running that heat continually. So things to consider. You may have to adapt your design to accommodate the water heater size and location. Great options are, as long as you're not in climate zone 16, locate it in a closet or a space within a garage attached to the house, outdoors, crawl spaces, attics. Those are wonderful locations outside of the conditioned floor area. When you can put them in the conditioned floor area, obviously heat pumps extract heat from the ambient air. So the warmer that ambient air is, the more efficient that unit's going to work. The colder, the opposite is true, the colder the air, the harder that heat pump has to work to extract heat from that air. So I was going to transition and just cover a couple of new requirements to our energy code come January 1. The 2022 code goes into effect. Are we okay time-wise? Jennifer?
Yeah, you're doing fine.
Great. So as I mentioned earlier, our 2022 energy code goes into effect January 1 of 2023. We always get the questions, how come it's not the 2023 code? Well, this is the year in which it's adopted, which it was adopted this year. It goes into effect. Implementation starts January 1, 2023. So you can download those standards, reference appendices, manuals coming soon. The Energy Commission's website, as well as Energy Code ACE, has a wonderful tool to view the code. It's called the Reference ACE. If you get a chance, check it out. Really great opportunity to resource the code and reference the code through that. So now I want to go through a couple of the highlights here. I'm definitely not going to cover the exhaustive requirements, and I apologize. I have non-residential standards up here. I promise you that these are our residential standards. I just caught that. But for the 2022 code, we're going to see a new compliance metric. Currently, we have, for new construction, we have an efficiency EDR metric and a total EDR metric. EDR stands for energy design rating. It's kind of like a miles per hour sticker or miles per gallon sticker on your cars. It's just a way to compare different buildings that might be designed differently or different climate zones and on apples for apples basis. So now additions, alterations are still looking at the TDV energy use of their standard and proposed. But for the 2022 code, they're introducing a new metric. It's called it EDRS, or source EDR rating. Source EDR rating, again, we don't have a lot of behind the curtain understanding of how the software is calculating this. We do have some definitions from the Energy Commission, but it's a separate metric based on hourly source energy. And what it does is it's going to establish a proxy for carbon emissions. We talked earlier about operational carbon, and that's really what this is designed to rate. So come 2022, not only are you going to have to meet the efficiency EDR compliance metric, the total EDR compliance metric, but also now the source EDR compliance metric that is going to address carbon emissions. So what that looks like, here's just an example of what types of features or factors are involved in each of these. So you can see the hourly source metric for carbon it includes the energy use that's going through our envelopes, the indoor air quality measures, HVAC, domestic hot water, and other unregulated. When I say unregulated, they're not regulated by our performance software. They're mandatory requirements. So plug loads, appliances, and other types of loads in our houses. And then efficiency EDR, that hasn't changed for the 2022 code. The total EDR, which is a representation score of the effect that our PV and flexibility measures have on our efficiency of our building. It has changed. The way they calculate that has changed, but essentially it's representing the same metric. So all three compliance metrics must be met for a new construction project to comply under the 2022 standards. Now, what that looks like on our compliance documentation, source EDR, our proposed design needs to be equal to or less than the standard design. Same goes for efficiency EDR and total EDR. If one of these is not in compliance, the whole building does not comply with the energy code. So really, we're looking at all the aspects, the efficiency of the building, the effect that PV and flexibility has on the building, as well as the choices for fuel and how that is going to impact our operational carbon emissions for that building. So this is cutting edge stuff. This has never happened anywhere else in the US. So we are literally on the cutting edge of energy efficiency in California. Now, moving on to our envelopes, just something I wanted to point out for our attic spaces. We talked about the below roof deck insulation requirement was prescriptive. 2022 code is going to make a mandatory below roof deck insulation in those hotter climate zones 4 and 8 through 16. So there is no trading off mandatory requirements. Essentially, that looks like either a roughly equates to about a R4 insulation below the roof deck, kind of over in this right-hand image, and R3 above the roof deck, roughly that U factor converts to. So it applies to the roof deck, so the top chord of our trusses, and it does not apply to the ceiling insulation requirement. That is a separate requirement. Depending on your climate zone, maybe R30 or R38 in those respective climate zones. So again, big impact it has on ADUs because of the potential reduced vertical clearance here. No exceptions, again, for mandatory measures. They got to be met. So there are no requirements for non-attic roofs. So if you have a rafter roof, you're still going to have to overcome the prescriptive penalty, for that, but it is a viable option still. Moving on to our electric ready requirements, we've had a whole new suite of electric ready requirements introduced to us. I'm going to go through these really quick. Now, if you're already installing an electric appliance, for example, if you're putting a heat pump water heater in, you don't have to do this. You've already met the electric ready requirements because you installed it. But for whatever reason, if the project is installing a gas appliance, then you have to make provisions to install the electric prescriptive equivalent in the event that the occupant wants to change it. So various requirements for wiring, minimum size requirements, condensate drain lines, and so forth. Also power requirements, depending on where that water heater's, the designated electric water heater is within 3 feet or greater than 3 feet, will determine what the amount of conductors and amp rating of that breaker needs to be reserved in the panel and also wired to that future location. And if it's greater than 3 feet, not only do you have to provide the electrical requirements, but you also have to route the plumbing by that location first before it goes to the gas water heater. So since we're all building electric buildings, this is probably not going to be a big issue, but just keep that in mind. There are some conditions that you would need to be met come 2022. So for furnaces, if somebody chooses to do a gas furnace, then you have to make provisions for electrical 220 volt branch circuit within 3 feet of that gas furnace. And really what that's designed for is a conventional central heat pump. And a lot of those heat pumps, not as many anymore, but require heat strips as supplemental heating to during the thaw cycle of that heat pump. So these are, again, making ready for the electric equivalents. You got to reserve space in the panel. Last time I checked, if somebody was going all gas, they would have to have like 7 or 8, maybe more breaker spots available. Those are 2 poles, so 220 volt breakers, and also bump up the panel size in order to accommodate all these electric ready requirements if they choose to go gas. Now, as far as cooktops go, if somebody goes with a gas cooktop, likewise, you'll have to run the electrical requirements for that future installation of electric cooktop. Likewise, for drier locations, if you choose to go gas, you'll have to also wire the equivalent. And every one of these must be wired. They must be labeled. There must be reserved panel or breaker locations in the main service panel for electric ready use in the future. So mechanical systems, not seeing a lot of changes here, but some very specific changes here I want to talk about. When I talk about mechanical, I'm lumping in the indoor air quality requirements here. Kitchen range hoods, if you have either a gas range or electric range, the airflow for that range hood is going to vary. They also introduced a capture efficiency equivalent. You can see if you have an electric range, you're going to be at the minimum airflow requirements, depending on the size of your dwelling. Once you move to a gas equivalent, gas cooktop, then you're going to have to increase the amount of airflow in order to capture not only the gas fumes, but it's going to be a much higher either capture efficiency or much higher flow rate in order to do that. Again, increasing the energy usage of the home. In addition, there's some minimum sizing for the ducting for our kitchen hoods, depending on whether it's a flex duct or a rigid duct and so forth. So now here's a big change in our code. For the 2019 code, we had our first ever option for what our baseline fuel is. If we choose to go gas, then our baseline for space heating and water heating was gas. If we wanted to go all electric, our baseline for those two categories is all electric. Now, that's changing for the 2022 code. Now it's based on the prescriptive requirement. So heat pump space heating is prescriptively required in climate zones 3, 4, 13, and 14. That means the other 12 climate zones have a gas space heating baseline. Now, you can always choose to do an all electric in those other climate zones, but if you're in climate zones 3, 4, 13, or 14, and you choose to use a gas space heat, you're going to be penalized heavily for this. So, and again, you could not comply prescriptively with a project in those climate zones with a gas space heating. Moving on to our domestic hot water systems, again, the prescriptive requirements are a heat pump water heater. There is an exception for those projects in climate zones 3, 4, 13, and 14 to use a gas tankless water heater. Just keep in mind, they're also going to have to plumb for electric backup as well. And it's a single 240 volt NIA tier 3 heat pump water heater or higher. You can do the tier 4s with the advanced control features on, or you do a solar thermal system with electric backup. You got to have a minimum 70% solar savings fractions to do that. So here's where the really nice exceptions come in for ADUs. If you have a dwelling unit that's 500 square feet or less, with point of use distribution, then you can use an instantaneous electric, which is a tankless electric unit instead of the heat pump water heater. So all those space issues we were talking about, the constraints about heat pump water heaters, this may be a really good option for you. Of course, you're probably going to use a little bit more energy than the heat pump water heater, but you kept an all electric building and you have the flexibility of that really compact water heater. So now the point of use distribution means that you have to be within a certain distance from the water heater, the source, to the outlet. Depending on the pipe diameter, you're going to have either 10 feet with a 3/8 pipe supply, I think 15 feet horizontal distance if it's a 1/2 inch. I think it's still 15 feet if it's even any larger. So now, additionally, with dwellings with 1 bedroom or less, you can use the 120 volt option for the heat pump water heater, not the 240 volt. So again, you have a little bit of design flexibility there. So additions, alterations, they don't apply here. There are change out requirements for alterations based on the existing fuel type, and those electric resistance point of use water heaters will never comply prescriptively for additions, alterations. So keep that in mind. Great. Moving on to our renewables. Again, not a huge change for the 2022 code. I'm just going to cover these real basic. We have a new acronym, SARA, Solar Access Roof Area. You can see what SARA does include. It includes the area of the building's roof space capable of supporting a PV system, and all of the roof space on covered parking areas, parking, carports, other newly constructed buildings, and so forth, could be considered part of the SARA of the project. SARA does not include any portion of the roof that has less than 70% solar access, meaning that if you're on the north side of a steep sloped roof, that's going to have very, very little solar access, probably way less than 70%. So That's not included in this ARA. So you can see some of the other requirements here. There are some wonderful exceptions, again, for steep sloped roofs between 300 degrees and 90 degrees. Again, you can't install solar on those. Anywhere where the SARA is less than 80 contiguous square feet, you can't install it. And here's the new one that is really interesting. When the minimum PV system size is less than 1.8 kWdc, that means these really small buildings with a really small minimum PV system size does not necessarily be required to install solar. Now, you can always install it. There's no penalty for installing it, but it does remove that energy code requirement to do that. There are many other exceptions listed in section 150.1 C14. So a couple more here, and this is going to be a good transition into our appliances. Configuration for battery ready systems or energy storage systems. There isn't a requirement to install a battery. In fact, there's a really nice credit if you do choose to install a battery, but all new construction projects starting January 1 will need to pre-wire for battery readiness. Not only that, they'll have to also install at least 4 branch circuits serving various locations in the building, including the refrigerator, 1 lighting circuit near the front door, 1 sleeping room receptacle, and 1 other one of your choice. The wiring has to be installed. All the panel breakers need to be met. So we've got some really great resources at Energy Code ACE. I'm just wrapping up here. This is our accessory dwelling unit quick reference sheet. So a lot of the things I'm talking about are included in here, as well as some virtual classes. We've got a live class for architects and designers. We have a special request training code breaker series on ADUs, as well as I've got several Code and Coffee episodes on our Energy Code ACE YouTube channel that specifically focus on modeling accessory dwelling units. So that's it, Jennifer. My contact information here. I'll turn it back to you.
Thank you so much, Brian. All right, Richard, we would really like to hear you talk about all electric kitchen design.
Great. Let me share up a screen and let's do it. And let's see. Right here and share. And I'm hoping that you're seeing the right screen. Hi, everybody. Brian, incredible. Amazing stuff. I was so glued to your presentation, I almost forgot that I was supposed to be presenting myself and was in the zone there. So, okay, let's get in and let's talk about this. Hi, everybody. I'm Richard Young. I work at this place called the Frontier Energy Food Service Technology Center, and I've been out there about 33 years. You can see this photo on the left of me in 1992, 30 years ago, when I was, there I am, testing gas and electric range tops. And then just a couple of years ago, this is a photo on the right is me at the Berkeley electrification event and demonstrating induction cooktops. And so I enjoy this field of work, obviously, because I've been at it for a while. And every day is a new adventure, and I learn something every day. But let's talk a little bit today about the notion of kitchens and ADUs. And this is a great photo from Charles, his kitchens, and his ADU. And thank you, Charles. This is the perfect lead-in because the first question I asked myself is, what's the function of a kitchen? What do you have in there? And when we were doing the prep for this session, that was some of what we were talking about. What is a kitchen? And, in an ADU or a small living space like this, it could be anything. The possibilities are endless on how you actually build a kitchen, but you do want a couple of, necessities there. So let's start from the notion of what you need in a kitchen. Refrigeration. So Charles has a little under counter refrigerator nicely designed into the wall unit. Beautiful, looks great. And this is such a well-designed little small kitchen. It's great. You want a cooktop so you can do some saute type stuff, make your omelets. You want some kind of oven so you can do some kind of roasting, broasting, reheating, that kind of good stuff. Once again, multiple formats. Of course, we're going to talk about the cooktop. And I love how Charles has the induction unit and he's got a drop-in unit there. And then you need that ventilation, as Brian was just talking about. We need to get the effluent out of the building. And I'm glad to see that residential exhaust hoods are getting some love, because, you know, for most of my lifetime, they have been miserable and not really done much at all. So I'm glad now there's some capture efficiency and people are working on that. Kitchen ventilation is a whole nother world. We could talk for hours about it. Other things you need in your kitchen, you obviously need some food prep space, which is kind of cool. I love the fact here that the induction cooktop is a drop-in into the counter, means that you could use that entire countertop for food prep. You could put a cutting board down and cut right on top of the induction cooktop, or, you know, whatever. You've got loads of space. So that's always the one headache for people, is food prep. And the induction cooktop gives you some benefit there. And of course, you need a sink for your sanitation, for washing stuff and cleaning dishes. Then you need some waste management, some place to put a garbage can. So Charles, I'm assuming that maybe you have a can or a recycling bin, right? Compost right there underneath the sink. That's where so many people put it. And of course, you need some storage. So if you can get all those things together in some format, whether it's on a sailboat or a mansion, that's what your kitchen is going to need. So we now know what the kitchen's looking like. Let's talk about why induction is perfect for ADUs. I think induction in America, the acceptance of this, the evolution of product, the availability of product, the fact that we're all talking about it is absolutely perfect. The time is now. And of course, induction's been used in other countries for years and years. So we're not talking some technology that's, you know, fallen out of the sky. This isn't unicorns. This is well-developed technology, but it is absolutely perfect for what you're talking about in these small living spaces. First, you've got, with induction, diverse form factors and price points. So if you have a real low-cost building that you're building, you can get a countertop induction unit that sits right on the counter. It's not going to cost you very much. It will perform well. You can get, well, I'll show you a couple of these form factors, but suffice it to say, you've got a lot of tools in the toolbox and many different sizes of induction cooktops, which really opens up the flexibility to design what your cooktop looks like, as opposed to what we're all used to, you know, that sort of slide in electric coil range top with the oven built in. It doesn't give you a lot of flexibility in your design. The other nice thing is you have low to no radiant heat gain to space with an induction cooktop. So you're in a small space, you know, Charles, I think you said 500 square feet or something like that. You don't want a lot of heat gain, you know, from the cooktop, roasting the cook. And I say low to no, because if you do have a quality ventilation system and it's grabbing that convective heat that rises up off of whatever you're cooking, then there would be no radiant heat out into the space, because induction cooktops don't generate any radiant heat. If that residential exhaust hood is like 65% capture efficiency, you're going to get some radiant heat into the space, but it is dramatically lower than what you get from a gas range top. Fire and burn safety, I think this is just probably one of the most important things, maybe the number one reason that induction is so good. I know you end up with, families, grandma, grandpa, aunts, uncles in these ADUs. You might have some elderly folks, which is, of course, where I'm headed right now. And you end up with people who forget to turn off the range top, forget to turn off the burner, or forget that something's hot and burn themselves, or drop a napkin down onto a flame. With induction, you don't have any of that. There's no open flame. So, the safety from actually touching something and burning yourself or setting your place on fire is really, really low to zero. And then, of course, there's air quality. No combustion means, no NOx. You still have to have, when you're doing any cooking, most of what's coming off of the effluent that's coming off is, animal fats or whatever. If you're cooking bacon, you're breathing a lot more, bacon juice than you are NOx. But if you get rid of the gas range, you've got no combustion, you've got no NOx. That just makes your air quality better. And in such a small and tightly insulated space, that's a bonus to me. And then, of course, easy cleaning is another thing. I love anything that's easy to clean. And coming back to that notion, if you have elderly people in your ADU, it just takes away some of the stress. And then, of course, after we get through all of that kind of technical stuff, induction just kicks butt. There's better performance. You get precision. I always give the example. I've got a great Meyer lemon tree in my front yard. I love to make lemon curd. The magic temperature for lemon curd is 180 degrees. Lemon curd, by the way, is basically lemon flavored butter sugar. That's why I love it so much. And but 180 degrees, I set my little induction cooktop at 180 and I just stir. I don't have to sit there and play with the flame. So precision, which means also lower food waste. I love to make omelets. If I make it on my induction, my omelets tend to come out better than if I try it on the gas range. I get more sticking on the gas range. You don't get any carbon on your pans. You know, if you're using your pans a lot, particularly over, you know, sauteing or something, you get this carbon buildup on the bottom from the gas flame. No carbon buildup on the bottom of the pan, and just really consistent performance. You know, from season to season, the induction is always going to work the same. There's no fluctuation in gas pressure. If somebody spills soup down in the burners on a gas range, then, you know, half the burners don't light up. And you got to poke them out with a toothpick. You don't get that problem with induction. So lots of benefits there. Looking at some of the form factors, as I said, we've got drop-in units. You know, let's circle this one. There's a drop-in like what Charles had. There's the slide-ins, and which is kind of the traditional if you want that approach. And then I love this photo over here where they've got a drop-in in kind of a radically different space. So once again, lots of flexibility in how you can put this. If you have a flat surface, you can put your cooktop in. Also Hvacs, many formats of Hvacs, from countertops to drop-in units. And I happen to love Asian cooking, so I'm glad for that, right? And I could see, I love this one on the top here where you've got the mixed, the regular flat induction cooktop and your built-in, you know, the bowl for the Hvacs. So, and then loads of different kinds of countertop units. So if you're in a small space and you're not doing the, you know, the beautiful kitchen that Charles did, you need something more pedestrian. Lots of countertop units that you can use, and in various formats, you know, like the ones with two hobs on them. I have a single hob like this that I love to pull out. So once again, lots of flexibility. Now, I do want to say something. You may, if you've got clients who are interested in induction, the tabletop units are a great way to get people to try it out and understand what induction is, because it really is a different way of thinking about cooking. You know, it takes a moment to understand that whole notion of precision, temperature, and the fact there's no flame coming up. So the tabletop units are great, but they are not as powerful as your full-size units. So I just always want to remind people that if you're trying out the tabletops, you're going to get a little more fan noise. I mean, there's more power in a concentrated box, so you have to have, it's going to be like a laptop. You're going to hear that fan noise. In the bigger units, you don't get the fan noise. And so always keep that in mind, right? That's not to diss the tabletop units. That's just if you're doing a demo or something, there is a difference there. So here's another interesting thing that I think is both a safety piece and, of course, an energy piece. When you lift the pot off of the induction cooktop, you know, it turns off. So there's no walking away and leaving a flame on or leaving an element on or anything like that. And of course, when it turns off, it's drawing no power. So you get kind of, you know, instant energy management. But really, from my mind, that is a safety thing. I had a friend tell me recently that her elderly dad, you know, he literally burned down his house because he walked away and left the burner on. So it started grease fire and it was a problem. And then here's the other thing, you know, we love this demo. So Chef Mark here in the video is cooking some fish. And, you know, he puts a napkin down on the cooktop, and of course it doesn't catch fire. So you can't burn your house down by dropping a napkin or leaving a wooden spoon hanging over the side of the pan. And the other thing you'll notice, which I think is kind of cool, Chef Mark is picking this pan up with his bare hand, and he's not having to use a hot mitt or anything. And most of us, you know, if we're cooking something in a pan like that, sauteing it, we know that pan handle is going to be hot. And that's because most of us have gas ranges. And with the gas range, you have a lot of waste heat that comes up around the side of the pan, that comes up that handle and heats the handle up. With the induction, we're just delivering all the heat right into the pan. The handle is out of the way. The handle can act as the heat sink, which it's supposed to be, and you just don't get that same heat built up in the handle. So it's much, much safer when you're handling a pan. And I think that's a really cool benefit. And then finally, the easy to clean. I love this. This is after cooking the fish, which had lots of butter in it, splattered everywhere. Chef just wipes down the top, you know, and I think that's just I I love a future where we save energy, we can do things with zero carbon, and it's easy cleanup. That's the future that I envision. Now, nothing is ever perfect, so let's talk about a couple of challenges. Adequate electrical supply for these full-size units is one of the challenges. If you have a really small space, limited panel size, or you're trying to go into a retrofit situation, as my own house, I live in a 102-year-old house in Oakland, and I'm currently trying to upsize my panel, and that's a big pain in the neck. At some point, I'm going to get my electrical all done, all the knob and tube gone, and I'm getting my full-size induction cooktop. But that is a challenge at the moment, because you're usually needing a 50 amp 220-volt breaker for a full-size, induction cooktop with an oven on it. Resistance to electric ranges. Hey, you like my pun there? This is a behavior change element. It's this notion of, oh no, I can't give up my flame. I actually think this one's pretty easy to overcome, but you do see this. There is a resistance to any kind of change. I don't want to change. I've used this, but we're working on that one. And then the other thing is, in order to overcome that, resistance to giving up your gas range, there's a limited amount of sort of hands-on training, demos, this kind of stuff for interested parties. We kind of had that machinery going before the pandemic, and then everything went virtual. And we've done virtual induction demos, but it's just not as fun as doing it in person. So we have resources for these trainings, and I'll mention that in a minute. So yeah, primary hurdle to consumer adoption is that when you say electric range, including induction, most people envision these speed coils. These things are awful. I don't wish them on anybody. They did their bit in time, but they're just not great. They just don't perform well. So it's really important when you're talking to people to emphasize the fact that induction is a completely different technology than these electric coil ranges. They are not related at all. In fact, because the induction is essentially creating an electromagnetic field that you put the pot into, it actually is more equivalent to a gas range, which creates a convective heat field that you put a pot into, as opposed to these electric coil ranges where everything is conduction, right? So super important that we make that difference. And in order to emphasize that, a couple of years ago, SMUD hired our lab at Frontier Energy to do a comparison of gas, electric coil, electric resistance with the glass tops, and then 3 different induction range tops. And you can get that report off of the SMUD website. And I gave Rebecca some handouts. Hopefully she can get a PDF to you so you can get to this great big long URL. If not, if you go to SMUD and go, type in SMUD and R&D, you'll get to the site. The other thing is, at the Food Service Technology Center, we recently added on another component to our general Food Service Technology Center, which is all about induction. So we'll be listing resources there, trying to demystify it. We've been doing this for a long, long time, and we're trying to get information out and help be a resource to everybody who's interested. Other resources, Chef Rochelle at the Monarch showroom in San Francisco, and she's also, if you want more information, her website is Kitchens to Life. If you've got customers that are interested in some high-end equipment, really want to see some good stuff, talk to Chef Rochelle. She does demos there. She knows how to get equipment and all this kind of good stuff. So Building Decarbonization Coalition, electrickitchens.org. I've been working with them and a lot of people for several years to help them put together this website and get information out there. So that's another resource. And then, of course, community choice aggregators and munis, including SMUD, East Bay Community Energy, Silicon Valley Power, Alameda Power, Sonoma Clean Power, Palo Alto, PCE, which is Peninsula Clean Energy. And then also I've worked with PG&E for a long time. And in fact, they are supporting my time with you today. So lots and lots of resources out there to try and help you move forward. Many of these utilities that I've mentioned, they have funding for demos. So contact me if you've got customers. If you're looking at demos, let's see what we can set up. And then I want to finally mention one thing. I'm in a working group that is trying to solve this problem of the amperage limitations of range tops in retrofit situations or in ADU kind of situations. And where, like I said, you normally need a 50 amp, 220 volt breakers for full size range. We're trying to figure some way to get that down to maybe 20 amps at 220 volts. So you can go into these existing facilities, are very small buildings with limited panel supply, and try and put in your induction cooktop with an oven on it. So stay tuned on that one. We're working with manufacturers, some various players and experts in this industry, and looking to see what we can come up with. So, and that's all for me. I'll say thanks. And we are, wow, right bang on the time. So Jennifer, I'll turn it back over to you.
Thank you so much, Richard. This was an amazing presentation from all our speakers, and we have run out of time for what we had planned for this session. So you will get your learning units if you do leave at this time. However, if you can stay for a little bit longer, we will try to answer some of the questions that were in the Q&A. And I'd like to start with Charles, because I know, Charles, you had there were quite a few questions asked of you, and you had mentioned that you would answer some of them live. So could you turn your camera on? And there we are. Hello, Charles. So Charles, let's see. Liz Gibbons asked a question: if you are in California local community choice aggregate for power supply, they are procuring new renewable power generation. Silicon Valley SVCE has procured 1.6 billion new power to date. And I don't think that was a question, but did you have something more you wanted to elaborate on that one?
No, I don't think that's a question. There were some questions I noticed about point of use or on-demand tankless water heaters. With the 2022 code, that's an option for the when we were designing this, it was not an option because they're electric resistance and they would not comply with the requirements. So, but there is a demand issue with those as well. Richard probably knows better than me, but I think they're going to draw at least 40 amps, maybe more. And that's if you've got a limited electric service, that's going to be an issue.
Mm-hmm. Mm-hmm. Brian, can you elaborate a little bit on that? About there were still some questions about the ADU requirements currently versus the ADU requirements for electricity that will be coming next year. And also someone wanted to know something about flat roof projects as well.
Right. Yeah, I could imagine there's tons and tons of questions. Yeah, my presentation really just covered a really brief, small area of highlights what's new for 2022. And some of the challenges were all based on the 2019 code requirements. So regarding water heaters, like Charles said, you can still get point of use or tankless electric resistance water heating to comply. It just, the amount of efficiency it takes to offset that is generally cost prohibitive. You would have to put several other improvements on the building to get that to comply. As far as flat roofs, there's no prescriptive option for flat roofs in our code. We're hoping that maybe by the 2025 code, we're going to see those back in. But again, it just means that you would have to use the performance approach. But just know that you're going to be compared to a building with an attic. So you're already at a deficit. So it takes some strategy, and I highly recommend engaging with an energy consultant soon at the beginning of the design stages. Otherwise, you may get to the end of your design and go, whoops, we need to change. So that's kind of a generalized response to that. So a lot more detail if you want to reach out to me directly.
Sounds great. Richard, maybe you can answer this question. What are the energy efficient electric dryers like?
Oh, I'm sorry, I don't know that one.
Does anybody?
Although, I mean, I've got
one?
a very energy efficient electric dryer in my house here, and it's and basically it's, you know, something I bought at a regular white goods store, and it works beautifully. And for mine, it's just it has a humidity sensor, so it's just not running, you know, stupidly. If the air dries up, then it cuts off. But yeah, I'm not really an expert on washers and dryers, as curious as I am about those.
Well, while I've got you talking, do you know the cost comparison between induction and regular electric?
Yeah, if you're looking at a full-sized, you know, range top and oven, if you went down to the Home Depot today, that the cost for the induction is probably about twice as much as what you pay for the, you know, say a glass top resistance residential range. So it's kind of a 2-to-1, but once again, there, you know, you could buy a very expensive glass top resistance range and a very low cost induction, and they'd be the same. But if you're sort of looking at the same manufacturer, make, and everything, induction still tends to run about 2-to-1, which is, you know, it's still a relatively new technology and there's less of it. I think more supply will bring that cost down.
And do you have any recommendations for a microwave convection vent?
I saw that and I was going to say, well, Charles, what did you get?
Charles did that. Either of you like to answer that?
We found a 24-inch wide microwave that, and I think there's like practically the only one on the market. You know, almost all of the microwaves are 30 inches wide. They're designed to fit over a 30-inch wide slide-in range. But yeah, finding small appliances for a little ADU is a challenge. I think Europe there's a lot more appliances in Europe than there are here, and some of those manufacturers I think are going to start offering products.
Mm-hmm.
One thing I will notice, you know, there's a product from and this is on the HVAC side of things. Hvac is a product from Italy, and it's like a PTAC packet terminal air conditioner, but it doesn't. It's not a through the wall model. You have two little 6-inch ducts, and it's completely factory sealed. There's less risk of refrigerant leaks, and they're also right around 3,000 to 4,000 BTUs, which is you know, closer to a proper size for a small ADU. Those were not available 2 years ago, but they're starting to become available now. And so I would have definitely considered one of those instead of the split system had they been available at the time.
So could one of you explain the hardwired thermostat requirement in addition to the mini split remote control? I believe that came up under Brian's session.
Yeah, I'd be happy to. It's part of the qualifications for the variable capacity heat pump credit. And it's just a condition that the Energy Commission wanted on those units. Typically, those units come with a remote sensor controller that's typically placed in a cradle on the wall. But when you take that remote and leave it in another room, in the bathroom, it can't work right. So they wanted it hardwired, fixed into the room where that fan coil was. That's the reason for it. So it's not a typical install. It's a special request to have a hardwired thermostat for a indoor fan coil of a mini split.
Thank you.
You're welcome.
All right. So there's a question here for Charles. Your attic rafter installation, about rafter installation and ventilation. Why would you introduce cold air into that insulated space? I guess it's because it's a vented attic still.
Yeah, well, not the energy code, but the codes require that attics be ventilated. So it's not a. So you've got the energy code says step it off full of insulation, but then the building code says you have to ventilate it. So Ryan showed one solution to that. We had a slightly different solution, but and had the contractor not put ducts in the attic, we wouldn't have had this problem, because we would, in that case, we would have had insulation at the floor of the attic, and that would have been adequate. But when they put the ducts up there, I had to go back to Brian, and he had to do some more calcs on, and the only way to get it to comply was to move to the, what do you call it, the advanced or high performance attic.
High performance attic,
and,
yeah.
So that was, someone asked the question, well, did you have to redo the energy calculations? And the answer was yes.
A couple of times, right? There is an option to do an unvented attic, moving that insulation up from the ceiling up to the roof deck. But in a lot of cases, it's not extremely cost effective. It really depends on the situation. So I know we ran a simulation with the unvented attic, and it just didn't pencil out. So yeah, so I think there are options, and don't stop with just one solution. There are usually many solutions, but they all come at various costs and impacts for sure.
Okay, great. Well, I think that's all of the questions that we have time for today. So thank you all for being a part of this session, and really appreciate it. I think it was a really good one today. So thank you all for being speakers today.
Yeah.
And Rebecca, I'm going to turn it back over to you for your closing statements. I do want to add just a couple of things before I send it over to Rebecca. I want to thank you again for this great presentation. For all of those who are still in attendance, if you've made it this far, the AIA California staff will submit you for your AIA CE credit, and it should appear on your transcript in a few weeks. As always, additional resources and tools can be found on the AIA California's website. More details about our upcoming webinars and how to register will be made available to you soon in a follow-up email. And thank you again for joining us today. We'll see you at our next webinar.
Okay.
You said it perfectly. Thank you so much, Jennifer. Have a good day, everyone.
Thank you. Bye-bye.